I'm Ryan Kazanciyan. I'm the Chief Security Architect for Tanium. I have about 12 years background in incident response, forensics, and penetration testing. Prior to my current role at Tanium, I was at Mandiant for about 6 years doing mostly IR work. And I'm also the contributing author to Incident Response and Computer Forensics, the third edition of which was released last year.
And I'm Matt Hastings. I have a very similar experience to Ryan, so I'm not going to bore you with my details, except that I'm not a published author.
Cool. So agenda for today, we'll do a quick background to cover what DSC is and why we chose it as a topic of research. We'll introduce the DS compromised framework and walk through a few different attack scenarios. We'll do some live, well, quasi-live demos, some videos showing it in action. And then we'll switch from kind of the red team angle to the blue team angle. We'll go from attack to defense and talk about the sources of evidence you could use to detect what we're presenting today. And then we'll wrap up with areas for future research and work. So quick show of hands. How many of the people in this room, and don't be shy, have ever heard of desired state configuration before? Cool. I was in the exact same boat. So this is kind of an obscure thing that only existed since like mid-2014. So desired state configuration is included with PowerShell 4, which is part of the Windows Management Framework 4.0, installed by default on Windows 8.1 and Server 2012 R2 and later. It's Windows' next generation configuration management platform. So it's instrumented via PowerShell. The thing that it uses to actually manage configurations and ingest them is a standard. It's the MOF Managed Object Format standard. So the same thing Windows WMI has been using for like over a decade. But it also has some distinctions from things like SCCM or group policy. Like it doesn't require Active Directory to manage or configure systems. A lot of people call it Puppet or Chef for Windows. If you are in the DevOps world, you might be familiar with those. They're not really equivalent insofar as DSC really implements the configuration layer, but not so much the front-end tooling and management layer, meaning Puppet and Chef is kind of like a full stack solution. DSC just does the configuration bit. And in fact, they're interoperable. Like Microsoft has released open source components that the Chef and Puppet guys have used to build interoperability between them. So you can manage DSC with Puppet or Chef if you'd like. So why do we care? What can DSC do? So the thing that got us interested when we stumbled on this is this list of capabilities right here. So at its core, DSC means enforcing a desired configuration state on a system over time. And the way it can do that is by acting on the system in a number of different out-of-the-box capabilities. So these are all the things that in a pure, clean Windows system you get with DSC. So you can download and create files, you can execute processes and scripts, you can create users and give them grants to certain groups, you can control services, change registry keys, install software. This sounds a lot like a command and control framework that a fully featured RAT would also implement, which is fine. I mean, any administration tool is not terribly different from a good backdoor, right? But this is interesting because it's actually built into Windows, and so it got us thinking, well, how could we use this in nefarious ways? So the way this works, and we're going to go into more detail when we talk about the tools we wrote to help facilitate this, but the higher level workflow for DSC is broken into 3 stages: author, stage, and implement. Author is when you create the configuration to do those things we outlined earlier. You get a MOF file, which is the thing that has the config, and then you basically stage it somewhere. And there's 2 modes of operation in DSC. There's pull and there's push. Push means that you have the config file and you connect to a remote host via something like Windows Remote Management, and you literally transfer the config over and it gets ingested by the system. Pull is the exact opposite of that. You host the configuration on essentially a IIS web server, and then the client system that you want configured retrieves it via web protocol, so HTTP or HTTPS. You can also stage it on a file share, and SMB can be used to retrieve it. As we'll allude to later, we actually chose pull server via HTTP as our mechanism because it's a lot like a real C2 server. So we consume and implement the configuration on the victim host, and then we go into this cycle that we've shown here of basically continuously, the client monitors its config for drift. So this is called consistency. And the system is designed to automatically determine has its configuration drifted away from what you are enforcing, and if it does, it auto-corrects itself. So it's like a self-fixing backdoor. and that's kind of cool. So just to set this out clearly, we're not presenting zero-day vulnerabilities. We're not really presenting any vulnerabilities at all here. We didn't find anything intrinsically wrong with DSC as designed or security holes in its implementation. Nor did we identify ways to do like privesc with it. So you have to be an administrator to interact with this stuff on your victim host. But what this is interesting as is a mechanism for the post-compromise phase of an incident, right? So you've compromised a target, and now you want to hide. You want to persist malware, keep it running, keep a user account there, and you want to evade detection. And so Windows has lots of like auto-run mechanisms and persistence techniques that have been used for over a decade, and this, to me, fits as one of these categories. The other thing we wanted to do is simplify the process by which you could use DSC for this purpose. It was really painful to figure this out and learn it, partially because it's so new and so there's not a lot of great documentation online. But we wanted to make it as easy as possible for a red team to just roll with this with like a cloud-hosted C2 server and a couple PowerShell scripts to run on your victims. And then finally, Matt and I have basically investigated attacks and seen attackers misuse persistence mechanisms for well over 5 years. And it always seems like we're a couple of years lagging from attackers. Like attackers discover a cool persistence mechanism, they use it for a while, and then finally the forensics and security community catch on to it and build tools and techniques to find it. Neither of us have ever seen this used in the wild before, so we thought it would kind of be cool to out a persistence mechanism, show how you could leverage it, but then also show how you could detect it, perhaps before it is even being used by attackers in the real wild. And so, yeah, I think we both agreed when we were deciding to pursue this that DSC is a really interesting persistence mechanism. If nothing else, what makes it distinctive is it's really obscure, it's very flexible in the ways you can interact with the host. None of the existing security tools like the auto-runs utility, for example, enumerate DSC config. And finally, the automatic reinfection capability is kind of unique, right? The fact that you can actually have this set up to reinfect a host if someone tries to clean it up and misses some very easily missed ways that this mechanism works by. So this is the basis of why we went down this road for our research. Limitations, as I alluded to just a moment ago, this is really difficult to use. Like this was Matt and I for about a month as we were putting this work together. So troubleshooting can be painful. We tried to alleviate that with our scripts, but you still may hunt for some very obscure PowerShell error messages as you work with this. It does require PowerShell 4 on both the victim and the C2 server. For the C2 server, that's not a big deal. Like all of our testing, we just spun up server 2K12 R2 VM with Google Cloud or Azure, so very easy to get that ready. On the client victim side, though, your victims are going to have to be running either that server OS or Windows 8.1 or later. Technically, you can upgrade Windows Management Framework to version 4 or 5, but as an attacker, that's a really cumbersome, noisy thing to do, so I didn't consider that in bounds. And then again, finally, you do have to have local administrator equivalent rights on the victim host to mess with any of this stuff. So this falls squarely within the realm of post-compromise persistence and not privilege escalation or anything like that. All right, Matt.
Thanks. So as Ryan mentioned, DSC is not something that's very easy to implement. We found that there's a ton of roadblocks and it's not very well documented. So one of the things we wanted to do was eliminate as many of the roadblocks as possible and then streamline the process for weaponizing DSC. And so along with our research, we're also releasing what we're calling the DS Compromise Framework. And what this framework is, it's a set of PowerShell scripts that allow you to set up a DSC, what we're calling a C2 server, build out different malicious payloads, and then infect your victims. So far to date, it's 4 different components, all different PowerShell scripts, which we'll go into detail. And it's publicly available on GitHub if anybody wants to check it out. One of the first design decisions that we had to make was the push versus the pull decision. So do we want our victim host to have to go out and pull configs, or do we want to rely on our C2 server to have the ability to push down configs? And it's pretty evident that we want to go with the pull mechanism. For the first part, it emulates a true C2 server. It also doesn't require a route to the internal host. So if you think about, if you have an Amazon EC2 instance, you have to have a route to an internal host to push a config. And that rarely happens. The clients will reach out over HTTP or HTTPS and post to a URI and then attempt to pull down a config on a defined interval. Again, this can be on the internal network, but since it has a lot of requirements in standing up the server, it's typically better if you roll your own and not try and infect an internal server and then try to put all the DSC components part of it. So how this process works is the first part is you actually configure your pull server, and we have a script for that, which we'll walk through an example of. You create your malicious payload, and we have 2 different types that we're supporting at this point. And then finally, you configure your victims to then go out and pull these configurations down. And you can create as many configs as you want, but the clients can only pull down and enforce a single config at a time. So in our first attack scenario, we want to persist malware. We want to infect the machine with backdoor malware. We want to ensure that this malware remains on disk. And that's really not exciting. Like, that's pretty standard stuff. But finally, we want to reinfect our victim if it's been remediated. And this reinfection occurs if the system is online or not. So if you take the system offline and remediate it and not remediate it properly, it will happily reinfect itself without you even realizing it. So we actually have a quick non-live demo that we want to show you guys, and I'll walk through it as we're going. So on the right is our C2 server, and on the left is our victim. The first thing we're doing here is we're creating a malicious payload. We're giving it the file that we want to exist and the path where we want it to be located on our victim. And then any arguments you want the process to run with. So we're going to use netcat because it was pretty easy, and we just want to pipe a command shell out to our C2 server. Okay, it now creates this unique GUID, and you need to save that because that's what the victim will actually use to then go out and download this payload. So now we're on our victim machine. Like Ryan mentioned, we're already an administrative user. We're now loaded in our PowerShell module. The file is in there, which is what we're showing you here, and the task isn't running. Configure victim. We're going to just give it the server's IP address and the GUID of the payload that we want it to run. Now you're going to see a bunch of messages that don't mean much. There we go. Okay, and within a few seconds, or now, we have a command shell coming back from our victim.
Yeah, back on the server, we had a netcat listener hanging out here, and it happens instantaneously, so the connection initiates because the malware was dropped and ran on the victim host.
Yep. So now what we're going to show you is a remediation attempt where we actually go in, delete the file, and then kill the process. And one thing to note is the consistency checker, which is the process, or in this case, it's a scheduled task. It runs on a predefined basis, and what it does is it basically says, have I deviated from my config? And if so, do I need to reset myself? And so what we're doing here is just manually rerunning this consistency checker. And so we're just forcing it to run. And now, as you can see, we start back up our netcat listener, and our victim machine is going to immediately create that reverse shell again. And it's been recreated, and our process is now back up and running. So that's just a quick demo of how you can ensure a file is both present on a victim and running. Yep, there we go. That's it. Okay. So what do we actually do? Now let's walk through the steps in a bit more detail and what you actually need to perform in order to get this to work. So the very first thing is configuring your DSC pull server. And what that requires first is the DSC service, which you can just add with a simple PowerShell commandlet. And what this does is this installs all the prereqs that DSC requires. It installs the DSC service. And then what you need to do is install the required PowerShell modules. This actually comes in a zip. You just unzip it to the location that you want, and then these modules are always available to you in PowerShell. And then finally, you run our configure server script, which is part of the DS compromise framework, and your server is ready to go. What the server script actually does is it initializes the DSC server with some optional parameters. So the 2 parameters that we support are the compliance port and the config port. The compliance port is the port that the server runs that listens for victims to check in to report how they are compliant with the various configs. And the config port, which is important because this is the port that the clients will actually reach out to, so they have to be able to connect outbound. And this is where the configs are being hosted by your server. And they both have default values. So now that we've got our config server set up, the next thing we need to do is create our malicious payload. The first thing we need to do is copy a local file, the local executable file, to our DSC C2 server. So this is the file that we want to persist on our endpoints. We need to first put it on the server. And the reason we do that is because we actually don't copy the file down from the config. We read it in as a byte array into the PowerShell configuration that then gets passed down. So the victim machine isn't actually pulling down the file. It has it locally stored in a byte array within one of the files that Ryan will talk about later. We then run our payload script, and then we output. It basically creates the MOF file that we need, puts it in the right location, and gives us the unique GUID we need to configure our victims. So this is what the payload script looks like. Again, this is the source file, evil.exe. That's local to our pull server. The destination path, that's where we want it to exist on all of our victims, and any arguments we want it to pass. And again, the output of this, we put it in the correct location for you, so you don't have to worry about it. But if you ever care, this is where they need to be. And we also generate the output MOF, and there's a checksum file that needs to be created that we also just create for you.
Yeah, this is part of why we did all that automation. Like, everything has to be exactly so. The checksum file has to be named the same as the GUID file. They have to be in the same directory in that path. The DSC server has to be configured to host it all up. If any of those fail, then the whole thing falls apart. So the script does this all for you just to reduce likelihood of error at each of those steps.
It's incredibly brittle, like super brittle. All right, so the next thing we want to do is actually infect one of our victim machines. And so we need to log into the victim, copy down our configure victim script, and run it just like you saw. The first thing that the victim script does is it actually ensures the WinRM service is running because it's actually required for this to work. If it's not running, it goes ahead and starts it up. So that could be a telltale sign if you see WinRM running and you don't expect it. It then takes the GUID and the server address as parameters, and then it configures the local configuration manager, or LCM, to use the remote pull server. After that, the victim automatically downloads and applies the configuration. The configuration MOF drops an embedded malware on disk, and it executes. And then now we have a backdoor, so our attacker can now proceed to interact with it. Again, this is the pretty simple configure victim script. One difference is it has to drop a file on disk temporarily in order to initiate the configuration. So for whatever reason, you can't just pass an object in PowerShell. It has to be written to disk. So we write it to the correct location and then delete it, but you have an optional parameter to put it wherever you want, and then we'll go and delete it for you. The LCM is pretty interesting because this is where you can define specific parameters that are required to do different things. So allow module overwrite. This is what allows you to update a config on the fly and then push a new configuration down. So if you want to take the same GUID and overwrite it with something new, the victim machine, if this is set to true, will automatically download the same GUID but apply the new configuration, which is really nice for like dynamic updating as well as dissolving configurations, which we'll talk about later. The configuration mode frequency is how often it's going to try and reset itself back to its config state. So every in this case 15 minutes, it's going to say, am I compliant with my configuration? If the answer is no, do I need to reset myself? And there's actually an undocumented minimum here, which is 15 minutes. The apply and autocorrect setting with the configuration mode is what tells it to actually enforce the config rather than log it. So you can say, if I'm not compliant, just log it to a file and then I'll check it later. You can send it to the event logs, you can do whatever you want. But this actually enforces it back to the known state. The refresh frequency is how often it's going to pull from the pull server, and then the refresh mode is telling it that we're going to use a pull versus a push configuration.
One thing to keep in mind is because of this design, in this mode, it will execute your payload every 15 minutes. So if you had like a dropper, you'd probably, and you were writing your own malware, you'd want to ensure that you had some logic check in there so that you don't just continuously try to reinfect the system over and over. It also could be any command, right? Like we're showing you dropping and running an exe, but you could just run a PowerShell command with an encoded argument like David showed earlier today in his keynote. So lots of flexibility there.
Yep. So now in our step 3, we now have a victim that's beaconing out to our attacker. Our attacker's interacting it through a reverse shell. So let's say we get detected. So now we have, Blue Team Taylor, who runs onto the scene because she's received a network alert of some command shell being piped across the network, and she does an investigation. She finds a malicious process, she finds the file, she deletes both of them, she runs auto runs, can't find a persistence mechanism, so she's like, I'm good. I did a good job today, and she just goes around, doing her thing. What she doesn't realize is that the consistency checker is going to run within 15 minutes after doing that and then reapply that configuration. So it's going to recreate the file from the byte array that we have stored in the MOF, and then it's going to restart the process because it's not going to find it running. One thing that we found out that caused us a lot of pain, we thought we were going to have to scrap this whole thing because we couldn't get it to work, is that if you're on a laptop, the consistency task is set that if it's on battery power, it won't work. It won't run the consistency task unless it's plugged into a hard power.
Yeah, there's a fun thing in Windows schedule tasks, it's conditions, and this is across the board for all tasks, where you can define whether a task runs when you're not unplugged in power, which I guess is smart, like you don't want to burn battery trying to do an update or something that you may not want to do while the system's remote. But
it should tell you it's not going to do it, though. Okay, so now our internal victim has reinfected itself when it runs the consistency check, and the attacker is back to reenacting with the backdoor. But at this point, this malware has been burned because it's been detected by the blue team. So the attacker is probably not going to want to continue to use it because, infosec Taylor Swift's going to just obviously come back in, delete the malware again, and have to investigate the system. So as the attacker, one of the things you're going to want to do is update the configuration on the pull server. So what you can do is actually update the malware that you want to use as your payload, but keep the same GUID and just replace that GUID. And what this allows you to do is then the next time that the victim system checks in, it's going to update the same GUID, the same configuration, just download new malware and execute it. And then that'll continue to go undetected until something gets alerted. And then you win. In our second scenario,
Matt was so excited about this, Jeff.
I was very excited.
It is a great Jeff.
We just want to create and persist an unauthorized account. So we don't care about backdoor malware, we don't care about a running process, but we do want to have a local admin on a system and have it persist even if somebody deletes it or removes it from a group. And you can absolutely do that with DSC. So here we have another quick video that we'll walk you through on how we're doing it, and then we'll just do a quick step through. Again, server victim, server on the right, victim on the left. So again, you see the members of the local groups, the local administrators group here, and you see the local users on this host.
So system's clean right now, only 3 accounts.
This again is on our pull server. We're going to configure a user here. Now, one thing to note, the user password is stored in clear text in the MOF, so don't use your legitimate password for this.
So same thing as the other payload, like you get a MOF file, you get the GUID for it, and then you configure the victim to ingest it. Same exact concept.
So then we just give it the server address and the GUID. This takes a little bit longer for whatever reason than the file writes. So this hangs for like 2 or 3 seconds. Don't worry, it's going to end up working eventually, or it'll crash and burn. It could go either way. All right, so this error did not error out. So now what we can do is we can look at the users again. We now see our evil user has been created, and then we look at the evil users' group memberships, and sure enough, they're part of local admins. All right, so now we're going to do the same task of remediating the system. So we're just going to delete the user and then force another consistency check. And sure enough, this is going to be a big spoiler alert. The user is going to get recreated automatically.
Yeah, and again, just to be clear, we're just not waiting 15 minutes in the interest of the demo. So running the task manually is the same thing as waiting 15 minutes. And yep, user's back on the system.
Yep.
And we did confirm, it validates both the user existence and the group membership. So if you demoted the user but kept it on the box, it would
put it back in the group. And then just a quick definition of what the script is doing. You give it the username, you give it the password you wanted to use. Again, this password is stored in a PS credential object in the MOF, but it's in a clear text format. We did that so you don't have to pass certificates back and forth because that gets really messy. And then you can give an optional group where you can say any local group I want it to be a member of, but default it's going to use administrators. From the output, you get the exact same thing as you would when you did the payload, where it generates the MOF and the checksum and then puts them in the correct location for you.
All right, so switching to defense mode or incident response mode, let's talk a little bit how to find evidence of DSC use and abuse. And I think there's 2 fortunate things here. One is that DSC is so infrequently used legitimately. just taking the sampling of this audience as an example of that, the presence of it or the use of it anywhere in an environment might be intrinsically interesting. Also, even the most covert persistence mechanisms are only so good as the sources of evidence and your knowledge to look for them. So it's actually, as cool as this is as a persistence mechanism, it's pretty easy to find if you know where to look. And so that's what we're going to try to cover here. So first on the network side, if you've got a web proxy or if you're doing any form of network monitoring that gives you the ability to inspect URIs that are egressing your network, you probably shouldn't see requests for resources named psdscpullserver.svc. This is the URI scheme for retrieving the configs in pull mode. You can see in the example here we have a GUID specified. So this is what the requests look like. This is what a so-called infected host is going to be issuing every 30 minutes as it tries to refresh its config. So unless in the very rare circumstance that you are legitimately using an external DSC server, you probably shouldn't see this. On the endpoint, the configured endpoint on disk, the config files all live in a directory under system32 called configuration. And they're all MOF files. You get one called backup and one called current. So like they sound, current is the current active configuration. Backup is exactly that. It's a backup of that in case current gets corrupt. And then you might see one called pending that usually goes away once a config is applied. And then there's one called metaconfig, which actually contains the configuration about what pull server to go to and what the refresh interval is and all that stuff. Finally, there's a file here called pull run log. It's a plain text file and it just contains a single row every time a pull occurs. In terms of evidence, this is actually not the best log, so I covered it here for thoroughness, but we have better logs that we'll show you in the eventing system. If you look inside the metaconfig.mof on any system, you'll find the URI to the pull server. So we can see the full IP address and location of that resource. So I should step back and say first that those files won't even exist if a system isn't configured with DSC. In other words, none of these MOF files will be present in the configuration directory unless someone's tried to use this. So even the presence of these files can be indicative that something's happened. And then looking inside this file can tell you what the server is that's providing the configurations. You also get the active config ID in the same file. So what happens on the file system during infection? Basically, we use the config victim to pull down the payload that ran the netcat64 binary as our first example, and monitored file system activity to just look at what changed while this was occurring, just to see all the files that were being written and touched and so on. So if you have a capability to monitor changes to files in motion and centrally log that, you could see this sort of stuff. So really to summarize quickly, a temporary file, as Matt alluded to, we drop on disk called pullconfig.mof is the first thing that gets dropped, and basically that contains the configuration for how the victim is going to use the pull server. The next thing that happens is that basically gets serialized to the metaconfig.mof, which is its like permanent home. The first time you configure DSC, scheduled tasks are created for the consistency check and for restart boot check. So it actually does checks at both times, both at the polling interval and then on reboot. And those tasks are, again, they're created, they have desired state configuration in their path. So if those get created on a system, it means someone was using it. And then finally, there's event log that actually captures all this activity, the DSC operational event log. So if you've got a SIM and you want to start monitoring the log to look for the use of this tool in your environment, as we'll show you in a moment, that event log contains lots of good stuff. And then finally, the rest of it is mostly just MOF files getting moved around. So you have a temp directory that Windows generates for a temporary holding place for the configuration itself, the payload. So that's called localhost.mof. It's in the subdirectory under Windows temp and then a random number. We see the malware file get dropped here. The localhost.mof is copied over to backup and current.mof. And then the system deletes the temporary files. The pull run log gets updated. And then the configure script that we added deletes its own setup MOF, and now you're done. So basically, even though it leaves evidence on disk, if you weren't monitoring changes, it's fairly covert, I think. The event logs are a good source because they provide very explicit evidence that someone is trying to set up a pull configuration or a push configuration on a system. And so in this case, when we run our configure victim script, there's a whole series of events, and you can look at the slides offline and see the EIDs, but it basically says this user SID is trying to send a configuration from this computer. So it might be local, or if you're using PowerShell remoting, it could be over the network. And then we have the events basically saying, hey, I'm going to this IP address or this server URL and pulling down this configuration GUID. It's probably a little small on screen, but that's really all these events say. So just like looking in the MOF file, you get the URI to the pull server and you get the configuration ID. So if you were monitoring these events and you wanted to look for like rogue server addresses or URLs in these event IDs, that would be another way to find this in use. More of the same in this slide. And then finally, the task scheduler registers the task, the DSC consistency task, during first setup. And then when when you update the configuration or change anything, that task likewise gets updated. And so you can see these events are captured in the task scheduler log, and again, might be a good thing to monitor in your SIM if you're looking for this. And then finally, you can use PowerShell itself on a victim endpoint to enumerate this stuff. So there's a commandlet called get DSC configuration that, just like it sounds, returns the current configuration. So in the case of the configure victim for malware payload, we actually can see here the byte array that Matt was talking about creating, and this byte array is what contains the malware before it gets serialized to disk. So this obviously looks incredibly anomalous on a system. And most hosts, if you don't have anything configured, this commandlet would return blank. More of the same here, so just additional chunks of our script that are embedded in the configuration, so you can see the start process with the command line and all that good stuff. For user config, so if the payload was to persist a user rather than to run malware, the output of this looks a little different. It actually looks just like a net user output almost. You see the username that you're configuring, the group name that you're persisting it under, and then the settings for like password policy and all that. So this is how you'd identify that someone persisted a configuration to keep a user account with a specific password on a host. And then finally, instead of going to the MOF files, again, you can use PowerShell to enumerate the local configuration manager. And this would be if you wanted to identify if a system is configured in pull mode or push mode and what the last config ID it retrieved was. So again, if this ever produces output like this, you know someone's configured the system to use DSC, and you could proceed to look in the MOF file to get the address of the server. That's one unfortunate thing. We didn't find any method other than looking inside the MOF file to enumerate the address of a pull server when a system is configured in pull mode. Like this does not output that. It only gives you the GUID and the configuration settings. And then finally, cleanup. So if InfoSec Taylor Swift wants to come and actually clean up the system completely and prevent reinfection during consistency, what you need to do is go to that configuration directory and delete all the MOF files. So that won't harm the system in any way. All it does is it basically says, you know, whatever configuration you were persisting, stop doing that. And so that will be cleared out, and 15 minutes will pass for consistency, and nothing will happen because there's no longer any persistent state. So note that we're not talking about, if you're familiar with like the SIM repository, like objects.data, none of this stuff is serialized in that. It's all just living in these MOF files. So pretty easy to clean up. So what's next? The first thing that we were thinking of when we were doing this research is, are we kind of going down a path for a technology that may end up being, you know, trashed if it never gets picked up or generally accepted? But we think that DSC is probably here to stay, and there's a few reasons for that. One of the reasons it hasn't become more popular more quickly, I guess, is that it's so hard to use. I think there's, in the past year or two, adoption of PowerShell by administrators and by blue team and red team practitioners has greatly increased. And I think that will eventually spill over into DSC, since they require, I mean, you need so much PowerShell knowledge to use DSC. Lack of easy to use tools has definitely been inhibiting. Also the fact that this only works with Windows 8.1 and Server 2012 R2 certainly has an effect if you're thinking about attack surface and the proportion of victim systems that you could use this on. Fortunately, at least as we said earlier, the server side of this is in your hands. You control the C2 server. It's just something you spin up in the cloud. So you just have to worry about picking victims that can handle the client side of things. Another reason that I think this is going to be increasingly widespread is Microsoft open sourced the DSC resource kit this past June. That has led to a lot of other tool adoption, including, as I mentioned earlier, Chef and Puppet having integration points with DSC. Also, DSC is required to do a couple of things in next-gen versions of Windows. So some of you may have heard of Windows Nano Server. Nano basically takes the concepts of Windows Core even further, and it's like an extremely lightweight, small instance of the Windows kernel with all the GUI layers stripped out and all of the unnecessary things, even like the capability to run MSI installers and like parts of the .NET framework. So minimal core, great for like small instance VMs, great for security. And DSC is actually the only way to manage those. So if you want to install software or configure a Nano server, DSC is the way you do it. So if Nano becomes popular, you're going to see a lot more of DSC. And then Windows Azure has a mechanism by which you can actually configure DSC scripts and inject them into virtual machines so that they are all configured the way you want, which is great if you're managing a fleet of VMs, right? Because you have a simple way to make sure that they are the software you want is installed and that they're configured right. From an attacker perspective, that might be a really interesting vector as well. Like if I hijack that mechanism to tamper with configuration settings, I might be able to impact a number of VMs concurrently from an external location. So that's an interesting path that we might go down. Again, I do want to stress that neither Matt nor myself have seen any of these techniques in the wild. Every couple of weeks I've been searching the internet and I haven't really seen anyone else even talking about this yet. That doesn't mean it's not happening, but we would be very interesting if anyone ever stumbles across this. So please do let us know. And again, we're hoping we can be good citizens in providing both the attack and defense side of things to help with the detection side.
So just like we hope that DSC is here to stay, we also hope that DSC compromise is here to stay. So we are planning to add some additional capabilities. The first thing that we'd like to do is add in more resource availability. So if you want to enforce a registry key, or for example, if you want to, instead of drop a binary to disk, use PowerShell injection to just run malicious code in memory, those are the type of capabilities we're looking to add here in the short term. The other thing that we're looking to do is modularize configurations. So I mentioned earlier, you can only put one configuration on a victim endpoint. So what we'd like to do is allow you to stack as many resources as you'd like into that single configuration. So if you want to have a binary that runs and have a user account that persists and have a registry account or a registry key that's always present, stacking those all into a single configuration is something that we want to support in the near term. The ability to auto-dissolve your victims. So for example, if you need to dissolve victims and go away, building in capabilities to automatically update config so that they go in and delete all the MOFs. And again, the dynamically updating of existing config. So none of this would be possible if we don't support updating a config on the fly.